April 5th. Woohoo! By the way, we will not divide polynomials in Algebra 1, in case you were curious. That's more of an Algebra 2 advanced math kind of concept. So in this class, yesterday, we learned how to add and subtract polynomials. Today, and for several days, we will be working with multiplication of polynomials. And so today's April 5th, we are multiplying polynomials. This is a really important lesson because it's the opposite process of something that I need you to be really good at before the end of the year. And that thing is called factoring. And factoring is the exact opposite of multiplying. So you can imagine, like, if you were a fourth grade teacher and you were trying to get your students to be able to factor tree a number like 12. That's a pointless lesson as a fourth grade teacher if your students don't know that 2 times 6 is 12 and that 3 times 4 is 12. So as a teacher, if you're like, gosh, what's wrong with these kids? How come they can't take the number 12 and tell me to put 2 and 6 at the ends of the branches, or 3 and 4? Well, the answer might simply be, well, that's because they don't know that 3 times 4 is 12. And so I equate that to this, because in order to get you to where I want you to be good at factoring, I have to make sure you're really good first at multiplying. And so we're going to spend at least a few days on getting really good at multiplying polynomials together, so that at some point in the future, when I ask you to start unmultiplying them, that'll go better. So don't write this part down. I would just tell you that where we're headed is eventually I'll give you something like this. And I'll ask you to factor it. And that won't go well if we don't, that one's not factorable, just for the record, but that will not go well if we don't understand the process that goes into building it. And again, the analogy is what I said before. If you can't multiply something together, then why should I possibly think you would know how to do multiplication backwards? So that's what we do today. And today, we're going to scaffold our way up from one very mildly annoying to severely annoying. So this has multiple parts. We're going to start the lesson with multiplying a monomial times a polynomial. And I always use the term polynomial just kind of as a generalization. Probably not a correct usage, but I generalize that to refer to anything that's a binomial or higher. So to start class today, we're going to take specifically a monomial, and we're going to multiply it by a 2-term or higher polynomial. So as an example, if I give you 3x and I ask you to multiply it by 4x minus 5. That is polynomial multiplication. In this case specifically, it's a mono times a bi. And I bet you already know the answer to this. How would we attack this problem? You would distribute. In fact, that's really all you're going to be doing for the next few days. It's just, it looks more intimidating as the problems get longer, but it's just distribution. So if I take the 3x and I distribute it, first hits that, what do I get? I get 12x squared. Thanks to those of you that said squared. Good job. When you power an x with another x, you got to acknowledge that with an exponent of 2. And then when I multiply the 3x across to the 5, I get minus 15x. And that would be the end of that problem. What's nice about mono times poly multiplication is that you'll never have more than one step. You just do the thing, and then there's never an opportunity for there to ever be like terms. And we can make these look as fancy as we want, but really it's just not much to it. So like if I put negative 4y squared, and we're going to multiply that by 2y to the third minus 2y plus 5. It still fits under the heading of mono times poly, so specifically a monomial times something. So as we distribute through, I probably won't color code this one, but as I distribute, my first answer right there is what? Very good. And that's important that we know those rules of exponents, that's a perfect time to add your exponents together. And then what is this one going to be? The second one. Plus 8y to the third. And then the last distribution all the way across makes what? Negative 20 y squared. It's okay. We're all entitled to have some brain farts. What's important is that you get the process. Multiplying a mono times a poly deserves about that much of our time in today's lecture. I'm sorry, what did you say? Yeah, and I'm going to write my problems so that our answers naturally will appear in standard form. So I'll generally write my polynomials in standard form. Your answers, regardless of how that goes down, make sure your answers are always in standard form. Okay? So I can't vouch for, I think most of these, yeah, they're already standard formed for you, so shouldn't be an issue. So that's mono times poly. Do you have any questions about that? Okay, so that's a pretty specific category of multiplication. Now we're going to branch into poly times poly. And to begin, we're going to talk about the most important one of all, which is bi times bi. And so that's a binomial times a binomial. And this is the one that you're going to see. I can say this without exaggeration. You'll see thousands of these before your educational career is over. The bi times bi is a big one. So we're going to spend a big chunk of our time working with these. So as an example, if I gave you just a standard, like a linear binomial, like 3x minus 4, and I asked you to multiply it by another linear binomial, like 5x plus 2. What this is it's just distribution. And you guys answered that question very quickly on that very first problem. I said, what would we do? And I heard many, many voices say, distribute. Good job. That's what this is. It's just what it is it's repetitive distribution. So I think of it like there are two workers and their names are 3x and negative 4. And each worker will have a set number of jobs to do. And that number of jobs is determined by the number of terms in the target parentheses, the target polynomial at the end. So think of it like this. 3x says, well, I'm not going to multiply by my buddy who's next to me. That would be weird. But I am going to multiply by 5x. And then I am going to multiply by positive 2. He's got 2 jobs to do before he can clock out for the day. So what is 3x times 5x? 15x squared. And then I'm still on red guy. He's still doing his jobs. And so he's got another job. He's got to go all the way across. What's 3x times 2? So I'm going to put plus 6x. And then I can take 3x and say, good job. You've worked hard today. You're done. And now it's negative 4's turn. And he says, well, I also have the same 2 jobs to do. I'm going to multiply myself by 5x. And what do we get? Right, and then I'm going to multiply myself by 2, and I'm going to get minus 8. You would. And unlike those mono-poly problems that we just did, poly-poly, you're going to get like terms. Just almost every single time. It's inevitable. Unless someone writes a weird one where it just doesn't come up, they're going to be there. So what I look at is then in the middle, I'm like, hey, hold on a second. You two guys are like terms. And so I need to simplify you. So my final answer would be 15x squared minus 14x. Good job. And there is a little shortcut if you've ever heard like your older brothers or sisters talk about something called FOIL, F-O-I-L. I will address FOIL with you, but not until we're closer to ready. So for now, we're going to view multiplication as exactly what I said, repetitive distribution. That's all it is. All right, let's do one more of the bi-bis. And then we'll branch out and make them a little bit longer. So another bi-bi could be, you guys want to write it or do you want me to write it? Okay, so let's do 4x minus 1 times 7x plus 2. It's a 4-step process. The number of workers is 2. The number of jobs is 2. Each worker, 2 workers, 2 jobs each. 2 times 2 is 4. So what's my first part of my answer going to be? 28x squared plus 8x. Very good. Those 2 answers are the result of 4x having done his day's work. Who's the next worker? What's his name? -1. And what is -1 times 7x? It is negative 7x, which I think of as minus 7x when I put it into my answer. And what is negative 1 times 2? And there, as advertised, is the inevitability, the like terms in the center. It is just x plus 1x, and I know that this far along in the year, we know better than to put ones where they don't need to be. So we're going to have 28x squared plus x minus 2. You feel comfortable with that? Okay. Now, we're going to move on to longer problems, and I'm going to show you a different organizational tactic that I started using a few years ago. I would recommend that you use it. It helped. I wish I had learned it or used it earlier in my career. I find that as the problems get longer, it helps to have a little bit of a better system as to how to keep track of pieces. So now we're going to do by times a try. If you understand fundamentally the process, I can make these as long as I want, and they really don't get any harder. They just get more annoying. There's a certain point where it's like, good God, dude. So let's take a binomial like 4x minus 3, and let's multiply by a quadratic trinomial like 2x squared minus x minus 7. So how many workers are there? How many jobs are there? So if 2 workers each have 3 jobs to do, how many jobs are there? Right. So this will be a 6-step multiplication process, and then 1 step of combining like terms. Again, years ago, I learned that there's a really nice, elegant, organized way to show your work. And so I'm going to color code again. I'm going to go back to saying, okay, worker number 1, your name is 4x. And all the things I'm about to write in red are a result of him doing his work. So when I take 4x and I multiply it by 2x squared, what do I get? 8x. Shoot, well done. And then when I take 4x and I multiply him by negative x, what do I get? Nice. And then when I take 4x and multiply him all the way over to the negative 7, I get? Nice. Now, I want you to note that 4x is done. He's clocked out. He can go home now and enjoy his Salisbury steak or whatever. He's done for the day. And now it's on to worker number 2, and that's negative 3. And I want you to note as I do this, so before you write anything down, you might want to look up at the board and just take this is a pro tip. It's going to help with the organization. It helps with finding and combining like terms. So when negative 3 multiplies by 2x squared, what do I get? And note where I'm going to write it. And you're like, well, that makes perfect sense. What a great idea. Because what we're going to do now is the problems get longer. If I can collect my like terms already in a logical way, adding them and finding them is easy. So take the negative 3 and also multiply him by the negative x. What do you get? 3x. You get plus 3x. And so notice again where I'm putting it. I'm putting it right where it should be, underneath its buddy. And then finally, there's negative 3 times negative 7, which is, and I'm going to stick that one off to the side because it really doesn't have anybody to go with. So in a case like this, I put a little addition line underneath it. And I tell you, especially you'll see with try times try, which is next, that having this system is really nice. So when I add my like terms together, I just go straight down, easy peasy. When you go straight down, what's my first term? Okay, now look, my quadratic terms are all ready to roll. How many do I get? Yeah, and then my linear terms are all ready. What do I get? Yeah, and then my constant term doesn't, yeah, he'll never have a buddy to go with. So you always find like your leading term and your last term, they're kind of like they don't have a date to the prom guys. Good so far? All right, let's do one more, and then I think you've got the hang of this. And that's, of course, you know where this is headed. Going to be a trinomial times another trinomial. And again, if you understand the process, who cares? We can keep going. We could do a 4-term times a 6-term. It's just, at some point, you're like just torturing kids, you know, because you don't see a lot of that. So if I take let's take a quadratic trinomial like negative 4x squared minus 5x plus 3, and we're going to multiply it by another quadratic trinomial like x squared plus x minus 11. How many workers? How many jobs? 3 times 3? It's going to take us 9 multiplication steps to survive the initial part. And then 1 step of just some nice clean combining. So here we go. My workers this time, I shall call that guy Mr. Red. second worker will be Mr. Yellow, and then the third worker will be Mr. Green. So they each have 3 jobs to do, and I'm going to be super neat about this. So first job there, what do we get? Negative 4x to the 2 plus 2. Nice job. All right, and then my second job for Mr. Red is right there. What do we get? Beautiful. And then negative 4x squared all the way across times another negative 11 plus 44x squared. So Mr. Red can check out for the day, clock out, go home, right? Hang out with his family. And now Mr. Yellow is up. So when Mr. Yellow does his first job, what do we get? Mm-hmm. And I'm sure you probably knew this was coming, but if you look up at the TV, you can see that I put it right where it needs to be under its like term. And then Mr. Yellow has his second job to do, which is nice. And he's still got one more job to do. And what does he get? Yes. And then we got the new guy. Mr. Green is like, hey, I showed up to help you guys today. Looks like you got a lot of work to do. So Mr. Green showed up and he's got his 3 jobs. So what is this one going to be? So I'm going to put it where it belongs. Plus 3x squared. It'll go right underneath all the other x squareds. What's his second answer? And then his third answer? -3. Yes, and if executed correctly, you look at this and think, okay, it's kind of Rastafarian looking, but you get the idea. There it is. It's ready to go. So let's add straight down. What's our leading term going to be? Negative 4x to the 4th. First guy and last guy are the guys that don't get dates to the prom, right? It's now when we head down the second column, how many cubic terms do we have?
-9.
Yeah, good job. So -9 of the cubics. Now add down your quadratic column. Yes, 44, I would do the pluses first. 44 plus 3 is 47, minus 5 is 42. So plus 42 of the x squareds. Now head down your linear terms. What do you get? And of course, your constant. Think you're good?
Yeah.
All right.